Welcome to our video on Pyansys, the Pythonic interface for ANSYS simulation software. Pyansys is a powerful Python package that allows engineers and scientists to interact with ANSYS simulation software right inside the Python environment. To name a few, you can interact with the MAPDL product, which is used by structural engineers inside Python using PyMAPDL package. You can interact with Fluent product using PyFluent, and you can interact with electronic desktop product inside the Python environment using PyAEDT package. To install these packages, you need to install them using pip. Pip is the Python's package manager, and you should have them by default along with your Python installation. You can check using a command prompt and enter the following command to check if you have pip installed. Once you have pip, select the package you would like to install. Go to the Getting Started section of that package. Here you will find the pip command to install this package. For example, to install the PyMAPDL package, all you need to do is enter the following command. A similar procedure can be followed for all the packages. With ANSYS products in Pythonic environment, you have access to numerous Python libraries, and you can use them together with your ANSYS simulations. With Pyansys, you can automate ANSYS simulations, extract data from ANSYS results, perform post-processing tasks with ease. This is an example of how you can launch an MAPDL instance from within the Python IDE. Look at how I create my materials. I create my geometry and I visualize them. And I mesh my geometry and visualize my mesh. You can even solve them and extract results using Python libraries like NumPy and plot the contours using open source libraries like PyVista. You can look at the solver output while it is solving right within the Python environment. Hence, you can automate the simulation end-to-end using Pyansys, amplify the power of ANSYS products using tons of open source Pythonic libraries like NumPy, SciPy, and so on. Here, let's try another example of a static cyclic analysis of a rotor sector. Let us begin first by importing the ANSYS Python packages. Let's launch an MAPDL instance. Now, I'm going to read an MAPDL database file containing the blade sector mesh and plot them. Next, I'm going to enter the pre-processing routine and make the mesh as cyclic. I'm going to set the material properties. The next step is to apply my boundary conditions. Initially, I'm going to apply a cyclic rotation of 1000 RPM. Next, I'm going to constrain the nodes radially between 0.65 to 0.72. The next step is to run my static analysis. Look, as my analysis runs, I can view my solver output directly in my Python environment. My final step is to plot the displacement results. You can look at the displacement contours in 3D. You can plot any result contour in a similar way. Let us look at a similar cyclic example of using mechanical product in Python environment with PyMechanical module. Let us begin by import statements. As you might have noticed, I'm going to use the PyMechanical package together with PyMapDL and PyDPF. If you could recall from the Pyansys product page, the libraries which I imported are the DPF, PyDPF core, the PyMapDL, and PyMechanical. The next step is to create an instance of mechanical in Python using launch mechanical. As you might have noticed, you can launch mechanical using batch or interactive mode using the argument false here. As a next step, I'm going to just extract the working directory of the mechanical. The next step is to set the unit system inside mechanical to Newton millimeters. I would like to import a known geometry from my local repository here. Let's assign a structural steel material property to the geometry which I imported in the previous step. The next step is to create a mesh sizing and mesh the geometry and visualize the mesh. So this is how the mesh inside your mechanical looks like. As a next step, all I'm going to do is create name selections for the application of loads and boundary conditions. And then I apply my loads and boundary conditions and try to visualize my loads and boundary conditions. This is how my load and boundary condition looks like. In the next step, I apply a command snippet to specify cyclic and I solve the model. Once the solution is complete, I extract the result file path and directory. This could be used to post-process subsequently. As a last step, I'm going to post-process my results using PyDPF module and look at the displacements. This is how the displacements in my blade looks like. Note, you can extract various results and plot their contours using DPF. You could as well do a lots of result manipulations using DPF package. And finally, I try to post-process results using PyMapDL package. This is how the expanded displacement results looks like. Note, you can look at the entire workflow in interactive mode by setting the batch argument to false.